In this lecture, we'll continue our discussion on direct proof, and I will see the third type of direct proof, and that is called as proof by cases or by exhaustion. So, this method of proving statement P conditional Q is possible only when P can be split into several cases R, S, T, so that P is equal to R disjunction S disjunction T, where this is a OR symbol or disjunction symbol. Okay, so here in this proof by cases or by exhaustion, if you want to prove a statement P conditional Q, then this statement P can be split into several cases like R, S, T, or it may be more than R, S, T, or it may be more than 3 cases. Okay, so that we can write P is equal to R disjunction S disjunction T. Okay, now we'll prove this. Instead of proving directly this P conditional Q, will prove R conditional Q, S conditional Q, T conditional Q. Okay, if all are proved, then R disjunction S disjunction T conditional Q is proved, and so P conditional Q is proved, because we have already written P is equal to R disjunction S disjunction T. Okay, so the method consists of examining every possible cases of the hypothesis. So it is practically convenient only when the number of possible cases are few. So this proof by cases or by exhaustion is only practically possible when this number of cases are few. So in this case we have taken 3 cases. Okay, and let's suppose the number of cases are few, then only it's practically possible. And if the number of cases are very large, then it's not practically possible to prove any mathematical statement by this proof by cases or by exhaustion. Okay, come to an example here. So we have to prove that if an integer n is not divisible by 3, then n square is equal to 3k plus 1 for some integer k. Okay, so we have, this is the initial statement. So this is an initial statement P, an integer n is not divisible by 3. This is the initial statement, and Q is nothing but n square is equal to 3k plus 1 for some integer k. Okay, so this P can be written as, statement P can be written as, okay, since n is not divisible by 3, okay, so P can be written as n is equal to 3t plus 1, or n is equal to 3t plus 2, okay, for some integer k. Okay, so we know that n is not divisible by 3, so it can be written as n is equal to 3t plus 1 or n is equal to 3t plus 2 for some integer k. Okay, so here we have 2 cases, n is equal to 3t plus 1 and another one is n is equal to 3t plus 2. Okay, so for case 1, n square is equal to, put the value of n as 3t plus 1, so we'll get 3t plus 1 whole square. Okay, so use the formula a plus b whole square. This is nothing but a square, that is 9t square, plus b square, that is 1, plus 2ab, 2 into a into b, that is 60. Okay, so it can be written as, take common here in this term and in this term, take common as 3, so this is 3t square plus 2t plus 1, so it can be written as 3k plus 1. So instead of 3t square plus 2t, you can write 3k. Okay, so here write down for some integer k. Okay, so this is the first case. Second case, so we have n square is equal to, put the value of n as 3t plus 2. So this is 3t plus 2 whole square. So this is equal to 9t square plus 2 square is 4 plus 2 into a into b. 2 into a into b is nothing but 12t. Okay. Now here it can be written as 9t square plus 12t. So this 4 can be written as 3 plus 1. Okay, so now take common 3 here. So this one is 3t square plus 4t plus 1. Okay, so it can be written as, instead of this we can write 3k plus 1 for some integer k. Okay, hence p conditional q is true. Okay, hence proved. Okay, so this is the original statement that is divided into two statement, n is equal to 3t plus 1 or n is equal to 3t plus 2. Then we separately proved each cases. Okay, so this n square can be written as 3k plus 1 in the first case. Similarly, in the second case, n square can be written as in the form of 3k plus 1 for some integer k. Okay, when you combine together, we proved that p conditional q is true. Okay, hence proved. So this was for today. Thank you.